An iron ball of radius 2 cm is heated for a period of 15 minutes from 25 degrees Celsius by an airstream at 200 degrees Celsius, flowing at a velocity of 20 meters per second. After 15 minutes, the heater is switched off and airstream is changed to 20 degrees Celsius, flowing at 10 meters per second for next 20 minutes. After this process, what is the maximum temperature attained by the ball? What is the final temperature of the ball after this complete process? Today, we will address these questions by simulating the model of this ball using Modelica. In this process, we will also learn some fundamental concepts of Modelica language. Welcome to Simulation Workshop, where we learn to build worlds through equations. This is the second session in a series of tutorials on system modeling using Modelica. Let's recap the problem statement. We have an iron ball of radius 2 cm that is heated for a period of 15 minutes, starting from 25 degrees Celsius temperature, and it is heated by an airstream of air at 200 degrees Celsius, flowing over a velocity of 20 minutes. After this 15 minutes, the heater is switched off and airstream is changed to a cold stream at 20 degrees Celsius, flowing at 10 meters per second for next 20 minutes. What is the maximum temperature attained by the ball? And what is the final temperature of the ball after this process? In order to answer these questions, we need to model this heating and cooling phenomena. So let's start with building the conceptual model. We have a metal ball staying at 25 degrees Celsius at start. It is heated for 900 seconds, that is 15 minutes, by a hot air stream. After this, the ball will attain certain temperature T1, which is an unknown. And after attaining 900 seconds, the temperature of the airstream is changed to 20 degrees Celsius and velocity is reduced from 20 meters per second to 10 meters per second. And it is continued for next 1200 seconds, that is 20 minutes. After this time period, the ball will again attain a new temperature, that is T2. Our objective is to find out T1 and T2 using the modeling approach. In order to start modeling, we need to understand what is the physics happening here. What are the fundamental governing equations that can build this concept? So let's understand what is meant by heating and cooling. When we say we are heating a ball by an air stream, what is happening here is that from the air, heat energy will be transferred to the ball through the heat transfer process of convection. Convection is mainly happening when there is a interaction between a fluid and solid surface. And it is governed by Newton's law of cooling. And as the heat enters the ball's temperature will increase. This is given by the first law of thermodynamics, where we can say that the product of mass, specific heat capacity, and the rate of change of temperature is equal to the total heat energy transferred from the object. Here, mass and specific heat capacity are parameters of proportionality, and temperature is proportional to the rate of heat gain. Similarly, when we say about cooling, the hot temperature will transfer heat back to the cold air stream through convection. This also follows the same rule of energy transfer as shown here. Also, the convective heat transfer is governed by Newton's law of cooling, which states that the total energy convected is proportional to the temperature difference between the solid object and the fluid medium and the surface area of interaction. Now, that constant of proportionality is known as the heat transfer coefficient, which is a complex parameter that need to be evaluated through multiple procedures. The theoretical formulation of heat transfer is a pretty involved process, which involves fluid properties, fluid velocities, and the determination of dimensionless parameters such as Reynolds number, Prandtl's number, and we have several empirical correlations such as Dittus-Boelter, Nelensky, etc. for finding the Nusselt number, which is another dimensionless parameter for heat transfer calculation. Nusselt number is often represented as a function of Reynolds and Prandtl's number. And the Nusselt number is defined as heat transfer coefficient times the characteristic length divided by the thermal conductivity of fluid. Rearranging the same, we can calculate heat transfer coefficient as shown here. Now, in this first example, I'm not going to go into this full detail of modeling heat transfer coefficient from fluid properties, but instead we can approximate this entire heat transfer as a function of the fluid velocity, assuming that the fluid property is remaining constant throughout the period. This is a rough assumption, but I believe this is good enough for our demonstrative purpose. Now, with this simplified equation, it is easy to find out the heat transfer coefficient corresponding to any velocity. Here the velocity is given in meter per second and heat transfer coefficient is given in watt per meter square Kelvin. We can see that the curve fit accurately captures the calculated value of heat transfer coefficient for majority of the range of application. So before we start modeling, let's take at some of the assumptions that we are taking for this modeling approach. We are using lumped capacitance approach as we are only considering a small ball of diameter 2 centimeter. For the lumped capacitance models to be valid, another dimensionless number, Biot number, which is given by the similar pattern where we have heat transfer coefficient, characteristic length, and the thermal conductivity of solid. This value should be lesser than 0.1 for lumped capacitance approach to be valid. In our case, when we evaluate the heat transfer coefficient for 20 meter per second velocity, from our polynomial equation, we will get that it is 78.23 watt per meter square Kelvin. Also, the characteristic length, which is given by volume by area of a sphere, once we calculate, we will get 0.0067. And the thermal conductivity is 54. So with this, we will get a value which is much lesser than 0.1. So we can say that the lumped capacitance approach is valid here. We can use the equations of volume of sphere, area of sphere, and the concept that mass is the product of density and volume to arrive some of the parameters that we need to build these equations. Let's recap all the values that we will require for modeling this simulation. We have the radius of the ball that is 0.02 meter, that is 2 centimeter. Density of ball, considering it is an iron ball, we are taking it as 7,850. Specific heat capacity of the ball is 502.4. Heat transfer coefficient at 20 meter per second is 78.23 from our polynomial. Similarly, for 10 meter per second for the cooling phase, we can calculate it to be 45.09. And thermal conductivity of the ball is 54. So now we have all the sufficient information that is needed to model. Now let's take a quick look at how we can implement this in Modelica. And let's try to understand some of the fundamental conventions and syntax for building models in Modelica language. Everything in Modelica is built as a model. And a model contains two sections separated by the equation statement. On the top part, we can specify our variables, parameters, etc. And after the equation section, we can specify our equations here. Now, model in Modelica resembles class concept in object-oriented programming, where we can create classes to represent models of physical objects. And models can contain instances of other models. For example, the model of a car can contain an instance of an engine model. Engine model can contain an instance of a piston model. So this helps in building systems of systems and arranging simple components to form complex systems in Modelica models. Also, each model can communicate with other models through interfaces or connectors. A switch can communicate with bulb and bulb can communicate back to the switch. This is ideal for building acausal connections that is common in physical systems. Also, there are some other type of constructors in Modelica, which are connectors, records, functions, package, etc., which we will cover in some of our upcoming sessions. But for the time being, we will be only using the concept of model. So let's start building the model. Now, we have two different type of entities that can exist in a model. One is parameter. Parameters are fixed values that remain constant throughout the course of simulation. They can be of any data type that is supported in Modelica. In this case, we are seeing a real variable. For example, if we are simulating the rotational motion of a wheel, the parameter can be the diameter of the wheel, which will not change during the course of simulation. In Modelica language, it is followed by the parameter keyword. The next important type is variable. Unlike parameter, real variable does not need any prefix. Once we define the data type and the variable name, it is considered as a variable. Variables control the flow of simulation, and they need to be defined at the start of the simulation, and they can be given an initial value using the initial equation section. But during the course of simulation, these values will be constantly updated through equations. And those equations will be represented after the equation section. In the example case of our rotating wheel, the linear velocity and angular velocity can be our variables. Equations connect the relationship between variables and parameters. Unlike conventional programming languages, the equality sign here does not represent assignment of right-hand side value to left-hand side value. Instead, it shows that the left-hand side and right-hand side are equal. So this has more mathematical meaning than programming meaning. And there is a very strict constraint in Modelica that when we define a model, the number of variables and number of equations in the model should always be equal. Variables can be connected to other variables and parameters using equations, or variables can take fixed values through equality sign throughout the course of simulations. So parameters cannot change during the course of simulations. Variables may or may not change during the course of simulations. We saw real variable type in the previous example Modelica code. But apart from real data type, which represent real numbers, there are some other types in Modelica. They are integers that represent integer numbers, Boolean which represent true or false, string that can store text information, and enumeration that can store a list of different arguments. Now, there are a lot of different derived data types such as temperature, length, mass, etc. They are all derived from these fundamental data types such as real. So temperature can be a real number. And there are several other parameters that are part of the Modelica standard library, which we will cover in later sections. Few other important aspects that we need to understand before we build the model is conditional assignments in equations. So here, if we see the T air value, that is the temperature of the air in our model, is assigned using an if-else condition. It says when the time is lesser than 900 seconds, we are just saying 900 because time is implicitly taken as seconds, then the value of T air will be 200. Else, the value of temperature will be 20. An important constraint in if conditions in Modelica is that an if must be followed by an else, because otherwise this equation will be incomplete in certain conditions. Because Modelica strictly adheres to the condition that the number of variables and equations should always be equal, so that every time, regardless of whether the time is greater than or less than or equal to 900, there should be an evaluation for this equation. Similarly, for heat transfer coefficient, if the time is lesser than 900, we are giving some value, else we are giving some other value. So this is an example case. Our real values of heat transfer coefficient are quite different. And another important thing that we should notice here is that other variables we need to define and define their data type, whereas time is an implicit variable in Modelica, which means time will be automatically declared and evaluated as the simulation progresses. We can use this variable wherever we need without having to worry about how we increment and when we start the time variable. Also, a very important section that we need to understand in Modelica code is the dir keyword. So as I said just now, that time is an implicit variable and it's automatically defined in Modelica. Any variable when passed to the function dir will return the time derivative of this variable. That means how the variable will change over time. That is given by dx by dt when we pass x to the dir function. So this comes quite handy when we have to model dynamic systems, because all dynamic systems evolve over time and we can automatically calculate the time derivative using the dir function. Now we have all the sufficient information that we need to build the model. Let's go to the Open Modelica connection editor interface and see how this is all put together and how we can simulate our model. For convenience of time, I have already compiled the model. We will go through each line by line and understand what it means. Every model starts with a model keyword followed by the name of the model. We can optionally import some of the standard components from Modelica standard library, or we can build our own functions. In this case, I am importing two sections. One is the SI module from Modelica units. Now, if you don't know where these are located, there is a left-hand side, there is a component library where we can search for components. And here, the Modelica Basics is a package which I created for consolidating these sample models. We will cover more details about how we can set up packages later. But what we need to understand here is the Modelica library. Once we open this, we can see modelica.units.si. If you scroll down, there is a unit section. Within that, there is an SI section. So within this, we have many different types of data types which are derived from our fundamental data types like real, integer, etc., which we covered earlier. Now, for convenience of accessing them faster, I'm importing SI. If you don't want to import, you can type the full path for these models and we can access them without having to import. It is just a matter of convenience. And also I'm importing a function from units that we can see here. In units, there is another module called conversion. And we can see that there is a function called from degree Celsius. Within Modelica, all calculations are done in Kelvin scale, but for our convenience, we want to pass values in degree Celsius. So this from degree Celsius function will automatically convert values from degree Celsius to Kelvin so that we don't need to worry about the conversion between Kelvin and degree Celsius in each step. With the two import statement, let's come to our parameter section. For this particular model, we need the radius of the ball, which is of type length, that is 2 centimeter, 0.02 meter. Type density rho, which is the density of the ball, which is 7,850. Specific capacity CP, that is of type real. Again, that is 502.4. These all three values we have directly assigned the numbers. We have equated them to numbers in the parameter section. Now, these two values, the parameter m and parameter a, which represent the mass and area of the ball. These are calculated using other parameters. So as this only involve parameters, they also become parameters because they do not change over time. An important point note here is that when you assign a parameter using a equation like a mathematical expression, you should notice that there should not be any variables on the right hand side because the variables can change over time. So the value of this expression can change. So the value of m should also change, but Modelica does not allow the value of a parameter to change over the course of simulation. So any expression that is used to assign value to a parameter should only contain constant values or other parameters. So here the expression for mass of the ball is 4 by 3 pi r cube, which is the expression for volume. Then we are multiplying that volume with density to get the mass. Similarly, for surface area of the ball, we are calculating it using 4 pi r square. This covers all the relevant parameters that require for the simulation. Now comes to the variables. So there are three variables that change over the course of the simulation. One is the temperature of the ball, which is created as a data type SI.temperature. Then we have another temperature, that is a temperature of the air, which instantaneously changes after 900 seconds. Then we have heat transfer coefficient that also changes over time period. So after 900 seconds, heat transfer coefficient also will change because the velocity of our airflow is changing. Now we have set up all the variables and parameters that we defined. Now since this is a transient simulation that proceeds over the period of time, we need to define what is the initial condition. When time is 0, what is the condition of our system? So as we have seen in our problem statement, the ball is initially at a temperature of 25 degrees Celsius and the starting airstream temperature is 200 degrees Celsius. So for converting degree Celsius to Kelvin, we can use the from degree Celsius function which we have imported earlier. And also we are assigning the value of 78.23 to our heat transfer coefficient at the start. So this completes all the prerequisites for defining our equations. Within the equation section, we can say that the total rate of change of the ball. So here we are using the der function for finding the time derivative of the ball temperature, and that is multiplied by mass and specific heat capacity. This is the convective heat transfer coefficient, convective heat transfer that is happening, and that is equated to the equation for convective heat transfer given by Newton's law of cooling. So we have the heat transfer coefficient, we have the surface area, and we have the two temperatures of ball and air. Now, as you can see, the left-hand side and right-hand side has expressions involving multiple variables, which is not common in a typical programming language where the equality sign implies assignment of right-hand side to left-hand side. But in Modelica, this only implies that this expression equals this expression during every time step. And the successive values of this temperature will be evaluated during each time step. Now, as you can see, since the two temperatures are different, which is 25 and 200, this term will not be 0. And we know that the area and heat transfer coefficient are non-zero. So this will have a finite value. And as a consequence, there is a change to the temperature of the ball because the rate of change of temperature is given by the derivative of T ball. As the mass and specific heat are constant, the temperature of the ball will change to accommodate this heat transfer. And every time when the ball temperature changes, this expression will be re-evaluated because the difference between air temperature and ball temperature will change, and the equation will proceed through each iterations. Now this iterating through time step will be carried out by Modelica, as we discussed in our previous video, how Modelica is different from a conventional programming language. Now there are two conditional expressions here. One states that the air temperature will change from 200 to 20 when the time step is greater than 900. Also, the heat transfer coefficient will change from 78.23 to 45.09 when the time step is greater than 900. So this completes all the physical or mathematical part of our modeling. Now we need to set up an experiment. So this is the model. In order to simulate a model, we need to set up an experiment. Within Open Modelica Connection Editor, we can set up our experiment using the simulation setup icon on the top. Once you click the simulation setup, it will open up a window which has several tags. We will cover the details of these tags, which are used for some advanced functionalities later, but let's stick to the general tab for now. So we know that the total simulation time is 900 plus 1200, that is total of 2100. So we have given the starting time as 0 and stopping time as 2100. And we are simulating it with an interval of 2 seconds for each iteration. The solution method is Dazzle, which is the default one that Open Modelica provides. There are a bunch of solvers available, but for the simple example, we will stick with the default one. Also, we can set up some experiment annotations inside the model, and we can set the simulation flag. So for this example, I just want to cover a few more things. So I'm not simulating this right away. I'm removing the simulate option and I'm just clicking OK, or I can even cancel, doesn't matter. I have already set up the configuration. Now, once you set up that annotation in the simulation setup, same thing we can also see here. For example, if we mark this save experiment annotation inside the model option, we can see the experiment being set up here. So here we can see start time is 0, stop time is 2100. Tolerance for the convergence, because this is a numerical method, we cannot get exact answer, is 10 to the power of -6. And we are taking an interval of 2 seconds. So either you can manually write this or you can configure it from the simulation setting. Now, a very important aspect that you need to check before running any simulation is the check model option here, which is given by a white tick mark on a blue circle. So once you check this part, your messages console will show that check of Modelica basics lumped heat transfer heat and cooling completed successfully, which is the path which I have created my model. So if you are creating it in a different path, it will be slightly different. I have created it in here. Now, if you are completely new to Modelica, you haven't done at all, you can just click new button and create a file and start coding this in it. Since it is somewhat trivial and there are many very detailed documentation available, I'm not covering the very basics of operating the interface, but we will cover, I can link to some of the basic introductory videos in the description. So very important consideration that we need to cover is that the number of equations and number of variables should be equal. So in this case, it has clearly shown that our model has 3 equations and 3 variables. So it's a balanced system and we are good to simulate it. Now to simulate, we can just click the green arrow mark which states to simulate. So I'm going to simulate. It may take a couple of seconds to compile and simulate the model depending on the complexity. Now we have simulated and it shows that the initialization is finished and the simulation finished successfully. Once the simulation is completed, earlier we were in the modeling tab where we wrote our equations and model. Now we will be automatically switched to the plotting tab and you can switch back and forth through the bottom right corner tabs. Now within the plotting tab, we will see an empty plot and the variable list on the right side. We have all the parameter and variables that are available here and their time dependent plot will be shown here as we select any of them. So now let's see how the air temperature changes with respect to time. So if you just click the variable T air, we can see the graph which states that the air temperature is 200 till we have the time of 900 second, that is 0.9 kilosecond. Since we are simulating for thousands of seconds, Modelica conveniently shows the graph in kiloseconds so that the values will be truncated to like 0.5, 1, 1.5, etc. Now this makes sense because we forcefully assigned our air temperature to vary at 900 seconds instantaneously without accounting for any physical phenomena. It is an instantaneous change and Modelica correctly captured the instantaneous change. Now let's see how our ball behaves. This is our point of interest. Now if you click ball temperature, ball gradually changes because we are incrementing the ball temperature using the time derivative and the convective heat transfer phenomena. So the ball temperature changes drastically at the initial state where the temperature difference is very high. And as the ball approaches higher and higher temperature, the heat transfer rate reduces. And as a consequence, the temperature change also slows down. Now, after the change of temperature from 200 to 20, the temperature again starts dropping further downwards and approaches the temperature as the time reaches 2100 seconds. So our maximum temperature attained here is 187.9 degrees Celsius and the minimum temperature, sorry, the final temperature which it attains after the complete process is something around 41.45. So these two were our point of interest when we started the discussion. Now let's see how our results are validated. As this is a very simple problem, we have an analytical solution for lumped transient conduction as given by this expression, which is derived by integrating the heat balance equation, which we discussed earlier, where the T is the temperature of the ball, T infinity is the temperature of the air, T0 is the initial temperature of the ball, and T infinity is same as the numerator. And we have the heat transfer coefficient, area, time, density, volume, and specific heat capacity raised to the power of E. Now substituting the values for heating mode, where the starting temperature is 20, like starting temperature is 25 and the air temperature is 200 and the temperature changes with respect to time. So we have given 900 seconds as time and we will see that the temperature value is 187.9, which aligns with the results we got from our simulation. Similarly, once we set up the values for cooling mode, where our initial temperature is what we got from here, and we calculate the time period of 1200 for cooling, we will finally get the temperature value of 41.44, which also is very close to what we saw earlier from our simulation. So this gives us confidence on our simulation model and allows us to investigate further the impact of geometry, how changing the radius will affect the time period and maximum temperature. This type of studies can be done using parametric variations of each parameter. So that's all for today's session. We carried out a very simple experiment using the model of a ball getting heated and cooled down. And as part of that, we covered some basic concepts in heat transfer, such as lumped transient heat transfer, convective heat transfer, conservation of energy, and approximation of heat transfer coefficient. Also, why it is important to have accurate information about material properties to correctly capture the simulation results. Also, from a Modelica side, we understood what are models, what are variables, parameters, and equations. Also, if-else conditions. That's all for today. We will see some of the more advanced features of Open Modelica and the power of Modelica standard library in our upcoming session. So see you soon. Till then, happy modeling.